Okay guys, we're picking up on 3.1 on day 2 here. This is not going to be nearly as long. I thought we could start by recapping what we did on 3.1 day 1. So let's go back up to the top here. First, we started talking about what extrema are. Remember, there are absolute, max, or min. Okay, we looked at some graphically, and then we went down to EVT. Now I'm going to reference EVT in our first example we're going to do today, so I want to touch on this again. What it's saying is if f is continuous on a closed interval, then it must have a max or a min. Remember, the biggest part I outline right here about this is just because the function isn't closed, a continuous on a closed, doesn't mean it won't have one. It just means that it's not necessarily guaranteed. Okay, and that's what that says right there. Okay, and then we went on and we looked at relative max or min. Remember, relative are different than absolute. Let's look at this graph right here. Relative just means in the area that you're at, is it the highest or lowest? So relative max is the top of the hill, relative min, bottom of the valley. Remember, relatives cannot occur at endpoints. So this is the lowest low everywhere. It's not relative because we can't compare it to the left. Okay, and a relative said to the left and the right, it either has to be higher or in this case, lower than everything else. You can have an absolute that is also a relative max, you see right there. Okay, we noticed at these relative max and mins that we had derivatives that are equal to 0. We went on to classify those as critical numbers. Critical numbers is where the derivative is 0, which is in that case, or undefined, which was at that cusp. We then went on to find critical numbers, and we didn't do much with them yesterday other than find them. So like right here was a critical number. Remember, if they ask for critical points, we're looking at ordered pairs. Okay, so now on to day 2. Now we're going to talk about how to find absolute max and min. Yesterday we identified them. We talked about critical numbers. Now we're going to talk about how to find them. First thing, identify the domain first. That's really important. Next, we're going to find critical values, which is what we did yesterday. Remember, a critical number is when the derivative is either equal to 0 or the derivative doesn't exist. Okay, if the derivative doesn't exist, that's going to be where the denominator of the derivative is equal to 0. If the derivative is 0, it's where the numerator is equal to 0. Okay, I'm going to go through these steps with you. I'm not going to read them all to you. I just wanted to point out that. Okay, so again, I recap because we had to talk about EVT. We have to determine if the EVT applies. Well, what was the condition? We had to be continuous on the closed. Look at this. Beautiful cubic, it's continuous everywhere. They gave us a closed. Okay, so EVT is good to go. Okay, also one thing, there's no domain restrictions, so our domain is going to be all reals. EVT applies. Why does EVT apply, guys? EVT applies since f of x is continuous on the closed interval. What is our closed interval? 0 to 6. Okay, yes, EVT applies. What does EVT do? It guarantees an absolute max or min. They asked us to find them when they say find the extrema. Okay, we're going to follow those steps up above. It said, did we have an okay domain or identify your domain? We did that. Okay, what was the next step? Going through these. Find the critical numbers. So we're going to find the derivative, set it equal to 0. Okay, so let's go ahead and find the derivative. So the derivative is going to be 6x squared minus 30x plus 24. Let's go ahead and factor this. If we take a 6 out, we get x squared minus 5x plus 4. If we keep factoring it, we're going to get x minus 1, x minus 4. What do we do with the derivative, guys, to find critical numbers? We set it equal to 0, and we find where the derivative doesn't exist. So in this case, we're going to set this equal to 0. We're so used to factoring, we have our answer, which is 1 and 4. Here's our critical numbers. Now, is there ever a case where the derivative doesn't exist? Look at the derivative formula right here. That's going to exist everywhere. Okay, so these are going to be our only critical numbers. This is where we left off yesterday, and we stopped here. But now we have to go on. What the chart says now to evaluate f at each critical number and endpoint. So absolute max and min can occur at critical numbers or endpoints. So that's what we need to do. So we're going to take x and f of x. Here's our next step. Our endpoints are 0 and 6. Our critical numbers are 1 and 4. So look at, they gave us endpoints and they gave us critical numbers. Let me show you why, and you can go back and look at other pictures, but what if I gave you this function? Do you see that this is where the derivative is 0? So those would be our critical numbers, but that's not an absolute max and min. They actually occur at the endpoints. Okay? Or we could have this function, and in this case, where is the absolute max? It's right here where the derivative is 0. Okay, the absolute min is kind of hard to tell. Let me do this. And then you can see the absolute min would be at an endpoint. So what this is saying is absolute max and min can occur at endpoints or critical numbers. So I'm going to test my endpoints and my critical numbers. Okay, so we're going to go ahead and sub these into this function. So we're taking all of these numbers and throwing them into here. I am not going to waste your time. You guys go ahead and do that. You can use your calculator if you want. But look at, if we throw a 0 in, you can see that it wipes all that out and you have 7. That's easy enough. 1 is going to be 18, 4 is -9, and 6 is 43. Again, you can check those on your own. Okay, once you're here, it's really easy to see. You're just picking the highest and lowest number. So here's the min, and here's the, that's not the max, that's the max. Okay, so F has a maximum of, what is the maximum? 43 when X is 6, and F has a minimum of -9 when X equals 4. Again, we knew we were going to have a max and min when we started this because EVT applied, which says as long as the function's continuous on a closed interval, we're good to go. If you guys looked ahead, you saw we're almost done, super short notes. Okay, determine if EVT applies. You are going to be EVT experts, I'm sure. Okay, EVT applies, yes or no, guys? Does it? EVT applies because f of x is continuous. Now, can we just write this without checking it? Let's go check it, right? What if EVT didn't apply? So look at this function. What this is really saying, if you need to see it this way, x minus 1 squared cube root. If I'm taking the cube root, anything inside of it can be negative. So I'm okay there. I have no domain restrictions. My domain is all reals. So yes, we're right. F is continuous on the close. Okay, let's see if you have these steps done already. What are we supposed to do to find the maximum? So backing up though, what does EVT do? EVT guarantees a max or min because we're on a closed interval. Okay, because we're continuous on a closed interval. So now, to find the max or min, we need our critical numbers, we need to test those in endpoints, and then we'll call it a day. So let's go ahead and find the derivative, which is the first step to finding our critical numbers. We have a derivative of 1 is 0. The negative is there. You take 2/3 down in front. You have x minus 1 to the -1/3 if you decrease the power. Please don't forget to take the derivative, sorry guys, don't forget to take the derivative of the inside stuff also. That just happens to be 1. Remember, that's chain rule. Okay, let's rewrite this. So we have -2, 3, and then we have the cube root of x minus 1 on the bottom. This is the derivative. Okay, how do you find critical numbers? You set the derivative equal to 0. Can this ever be equal to 0? No. Why not? -2 can never equal 0, right? What you're doing to set this whole thing equal to 0 means the top has to be 0, and that never happens. Now, what is the case when the derivative does not exist? The derivative does not exist when the bottom is equal to 0, because we can't have 0 in the bottom. You can see you divide by 3. Can you see x has to be 1? If you want to, you can cube both sides, but 0 cubed is 0, so x minus 1 is 0, x is 1. We only have one critical number at this case, so now we're going to test them. We're going to sub them back into the original function to see who wins. -1 is an endpoint, 1 is a critical number, and 2 is an endpoint. If you sub a 2 into here, 2 minus 1 is 1, 1 minus 1 is 0. If you sub a 1 in, that's also going to be pretty easy. 1 minus 1 is 0, so we have a 1. Now, if you sub a -1 in, you're going to need a calculator. If you sub a -1 in here, you're going to get -2 to the 2/3. So I'll let you guys, again, try the calculations on your own, and you end up here. Now, EVT guaranteed a max or a min, but this question only asks for a max. So let's just go ahead and answer it. We have a max of, what's our max? Well, it's the highest y value. So we have a max of 1 when x equals 1. Oh, I thought we'd be under 10 minutes. We're just a little over. Okay, let's wrap it up. If a function has critical points, do the critical points have to produce relative extrema? Can you guys think of a function who has a critical number that is not a relative extrema? Pause and try to think of one, and then I'll show you. Okay, I'll say, no way. Just because it has a critical number, that does not have to be a relative extrema. Can you guys think of this function? The derivative is 3x squared. If I set this equal to 0, if I'm trying to find a critical number, x is 0. But you guys know what this cubic looks like. Right, look at 0. Is there a relative extrema there? No way. So just because you have a critical point, that does not mean it has to be a relative extrema. We do not have a relative max or min here. Also, look at this. Do you see how the derivative is 3x squared? Isn't this guaranteed to always be 0 or positive because we're squaring it? If we're guaranteed to have a positive derivative, doesn't that mean the function's always increasing? So we'll never come up to come down to have a relative. Okay, kiddos, see ya.